Hello, my science lovers. This is a ScientistMel short, so it's a shortened version of one of the longer topics that I have on my live stream. So if you are not a person that's a fan of going back and watching live streams, fear not. This is a shortened, condensed version for people who are short on time, and today we're talking about lightning. So let's go ahead and get started. So for this particular episode, we are going to talk about the awesomeness that is lightning. So lightning, what is it? How does it work? And what are the statistics associated with it? That's what we're going to talk about today. It's generated from potential differences within the cloud, often from what we call cumulonimbus clouds, also CB clouds as seen on the interwebs. The stronger the field, the more likely there is going to be a chance for ground strikes. So what is this potential difference? Well, customarily, air acts as an insulator. So in the initial stages of development, this air that's acting as an insulator between the positive and negative charges in the cloud, in between the cloud and the ground, well, as these differences in charges increase, that air that's normally an insulator breaks down. And so then what happens is we have a rapid discharge of electricity, and that's what we call lightning. Now, lightning can occur between opposite charges in the cloud. This is called intra-cloud lightning, or between opposite charges on the cloud and the ground. This is called cloud-to-ground lightning. Now, cloud-to-ground lightning is divided into two different types of flashes depending on the charge in the cloud and where the lightning originates. Let's cover ground strikes, because that's the thing that really, we get like, oh my gosh, I don't want to get hit by lightning. So, well, how does this happen? The Earth is normally negatively charged. Now, below what we call a negatively electrostatic induction, or a big fluffy cloud that has a lot of charges going on in it and that potential difference. So this creates a section of positive charge on Earth. Now, between the cloud and the Earth, we end up getting what we call a huge capacitator. Now, as I mentioned before, the potential difference between charges becomes so great that there is a domino effect of breakdown within the cloud, and electrons start jumping in among the air molecules as that air insulator now aids the potential difference between positive and negative charges. Carrying on with ground strikes. What we have here is a leader, dart leader. It starts to come out of the cloud, and it's a bit erratic and doesn't really have a potential target just yet. And it isn't really attracted to anything outside of the overall positive charge on the ground. So it's not really attracted to anything particular outside of the ground itself. So once it reaches a close proximity to the ground, what they call a step or two, the electric field undergoes an immense amount of stress. Now, any objects on the ground are a potential target at this point, especially if they disrupt that field. This can be people, buildings, trees, as they can emit a positively charged streamer. So, normally we say, be a positive person, but you really don't want to be a positive person in the middle of a lightning storm, because you're going to attract the lightning. Now, a connection can happen between that streamer and that particular lightning leader, dart leader. What that happens is the stroke that we see is observed as the charge moves back up that ionized channel and returning to the cloud. Now, a peak current for a return stroke can be over 100,000 amperes. Now, this return stroke may not necessarily discharge that cloud completely. Therefore, dart leaders can cause a flickering effect. That's those little fingers that we see kind of darting off on the side. Now let's talk about this really cool thing called ball lightning. John Lowke, L-O-W-K-E, a CSIRO scientist, has developed a new theory focusing on how ball lightning occurs in homes and in planes. He also looks at it how it can pass through glass. Now, if you're not familiar with ball lightning, it's like this particular glowing orb that seems to be hot, and it can actually travel through glass, and you can see it go across airplanes. It's also called St. Elmo's fire. Now, his theory suggests that ball lightning is caused when dense leftover ions move to the ground after lightning strikes. So you have a lightning strike hit, and then here's all these leftover densely packed ions. They just go whoosh. Now he says, this is quoting him, a crucial proof of any theory of ball lightning would be if the theory could be used to make ball lightning. This is the first paper which gives a mathematical solution explaining the birth or initiation of ball lightning. Ball lightning is still pretty elusive to scientists, and they're still trying to work out the mechanics of how it actually happens. Now, Loki, L-O-W-K-E, it might be Loke, and if it's Loke, I'm sorry, but we had Thor earlier, so I thought Loki might be cool. He suggests ball lightning happens in homes and airplanes when a stream of ions grows on the outside of a glass window. The result is an electric field on the other side, exciting those air molecules to form a ball discharge. This ball then has a driving electric field of about 1,000,000 volts. So what it looks like it's passing through the glass, what it's doing, it's initiating this ball discharge on the other side of the glass by exciting those particular air molecules. So that's some pretty groovy stuff, huh? So, a little bit more about Loki, or Loke. He continues saying, other theories have suggested ball lightning is created by slowly burning particles of silicon formed in a lightning strike, but this is flawed. One of the ball lightning observations cited in this paper occurred when there was no thunderstorm and was driven by ions from the aircraft radar operated at maximum power during a dense fog. Now, he based a lot of that information on Air Force pilots who have seen this particular phenomenon, but no lightning storms were around. Now, Loki's paper is the first to present a mathematical solution explaining the occurrence of ball lightning using standard equations for movement of electrons and ions. So he's able to use physics, math, and chemistry in order to explain how this can potentially happen. Now, he himself says this paper is unique in that it not only explains the formation of ball lightning, but that how it's possible that it can actually pass through glass. So a really cool website that you can check out, it's called lightningmaps.org. Now, this isn't a live feed right here, but if you do go to that particular website, you can check out current lightning strikes all over the world. You can zoom in and zoom out and have a look and see where lightning is hitting. So that's a pretty cool website, you can check out. And if you're curious about my sources and you're like, where are you finding all of this stuff? Fear not, because you can go to my website, ScientistMel.com. All of my slides are there. You can download my slides, find my links, click on them, and go right to the source. Okay, so some particular facts and stats in regards to lightning. Cloud-to-ground lightning is common. Approximately 100 strikes every second can contain 1 billion volts of electricity. Can travel at 200,000 miles per hour, and each segment, that leader and dart leaders, are approximately, they can get to around to 150 feet or 46 meters long. Return strikes can travel 200 million miles per hour, and most lightning never leaves the clouds and can travel between them. So most lightning we see is intra-cloud, not cloud to ground. Rare forms of lightning are caused by extreme forest fires, snowstorms, and even volcanic eruptions. Now, in the U.S., lightning kills about 100 people each year. However, in 2017, there was an all-time record low of lightning only taking the lives of 16 people. Hey, it's a funky thing, but, it's just one of those interesting things about science. FEMA estimates the odds of being struck are 1 in 600,000. Florida has a high rate of lightning strikes, and they also have about 1.4 million flashes per year. So at Disney World, it's really, really, really important that you don't get on that roller coaster. And one of the reasons why they tell you, no, we're not getting on the outdoor roller coasters or any of them with water. It's a bad idea. Now, New England has only a few. And California has about 85,000 strikes per year. So if you're at Disneyland, you don't want to be on a roller coaster in a lightning storm. Now, something that's pretty interesting, there's a tiny Central African village called Kifuka, and if I say that wrong, I'm terribly sorry, and it is hit by lightning about 158 times per year. No other region of the world, no town, no village, no other place gets hit by lightning that much in 1 year. And so what do you do in regards to lightning strikes? If you're in a lightning storm, where do you go? Best place in the world is your car. This is what we have when we have a Faraday cage. Yay for Faraday. Faraday is absolutely amazing in that Faraday showed us, he's like, hey, here's this steel frame. And if you don't touch the steel on the inside, you'll be okay. So the steel frame can protect you from the lightning. Now, it's not the tires. Rubber is not the best insulator, and farmers while on tractors, they're like, I have rubber wheels. I won't get electrocuted. Oh, honey, they still get struck by lightning. But if you're in the car, don't touch the metal. The lightning travels on the outside, but it won't affect you as long as you're not touching anything metal on the inside. So you can protect yourself and your loved ones just by hopping in a vehicle and in a lightning storm. And somebody asked on the live stream, I thought it was a good question. If you're out in the middle of a field, try to find the lowest area possible. Don't be on a hill. If there's a hole in the ground, concave, lay flat in that. That's better than standing up straight. So lightning, it's generated from potential difference. Different types of lightning are intra-cloud and cloud to ground. We have leaders and we have leader darts, and they all kind of like those fingers that come off the lightning. Ball lightning is amaze balls. And now we have math that can kind of lead us towards more lab experiments to see if we can generate ball lightning in the lab. We talked about all the stats and what to do in regard to those particular situations involving lightning. Here are all my sources, and I don't expect you to read them all. But guess what? You can go on my website, ScientistMel.com, and on that particular website, you have access to all of my slides, all of my sources. You can dig down deeper, and if you have questions, ask me in the comments here. Or you can ask me on Twitter. I'm on Facebook. I'm everywhere on the internet, and I am on Google Plus as well. And so I'm going to take a moment to thank my patrons. Thank you, Tony, James, Lauren, Jen, Carl, Melanie, Patrick, Daniel, Paula, Tim, Carrie, Cersei, Keith, Zachary, Tony, Graham, Dragnot, Jennifer, Corey, and Heavy. Thank you for contributing to my Patreon account. If you like what I do, buy me a coffee every month. And if you can't do it every month, guess what? I got a PayPal, and I now have merchandise associated with my show. And it's exclusive artwork from an artist called Arc. I do compensate her for her work because I believe in paying artists for their work. So help a girl out. Help me boost scientific literacy if you can. If not, subscribe, share the word. I want to get out there and help individuals. Here's everywhere you can find me. ScientistMel.com, Patreon, Periscope, YouTube, and Facebook. And that has been the Science of Lightning Shorts version. Thank you so much for being here. I hope you enjoyed it. And don't worry, all of my shorts are organized in playlists. So you can always just click on that and check out all of the different sciencey things. Thank you so much, guys. Have a super fantastic day.